So let's take a look at ones that are very similar to number 111, K, L, M, and N. And in these cases, these are all examples of geometric sequences. Okay, remember, a geometric sequence is a sequence whereby each successive term in the sequence is found by multiplying by a fixed value we call R usually, right? So for example, I could have a sequence that begins with, say, 1, and then if I multiply, maybe the value of R is 1/3, I'll get 1/3, and then 1/3 times 1/3 is 1/9, and 1/9 times 1/3 is 1/27, and so on. So there would be an example of a geometric sequence, and the general term for this sequence would, probably can be written as what? Just 1/3 to the n. And in this case, since I'm starting with 1, I want to do 1/3 to the 0. When n is 1, I can do 1/3 to the n minus 1 if I'm starting with n equal 1, right? So this would be the general term of the sequence. I could also do just 1/3 to the n if I start with 1/3. All right, so at any rate, there is an example of a geometric sequence, and the idea is the value of R can be any real number. And so what we learned in the lecture, right, is, of course, if the value of R is between -1 and 1, in other words, an absolute value, it's less than 1, then the limit of such a sequence is always 0. So even if R is, a -1/2 or -1/3, I mean, if R was -1/3, what if we had -1/3 here? All right. Well, what would happen is we would have +1, but then -1/3, negative times negative, +1/9, negative times positive, -1/27. They would alternate between positive and negative, but the limit would still be 0. Okay. Graphically, what would be happening in that case is, right, if we plotted this sequence, right, we start with 1, it's equal to 1, and then at 2, it's equal to -1/3, so it's down here, and then by 3, we're +1/9, so real close to the x-axis. We keep bouncing back and forth, but we're kind of getting closer, right, to the x-axis. We're taking the limit is 0, so we're going to get closer and closer to that x-axis, even though we're bouncing back and forth, between the positive and negative values. Okay, bottom line is the limit is going to be 0 if the value of R is less than 1 in absolute value. If R is equal to 1, of course, that means what? Whatever our first term is, if R was 1 here and I started with 1, it would just be 1 times 1 is 1, 1, 1, 1, 1, 1, right? So limit is the first term in the sequence in that case, right? And the sequence would be convergent. So for example, if we have a sub n is equal to 3, which just means, right, 3, 3, 3, 3, 3, right? I'm multiplying by 1 each time. So in a sense, it's a geometric sequence. The limit is just 3, right? We're just staying at 3 all the time. If the value of R is greater than 1, then the limit is going to go to infinity. Think about 2 to the n, right? 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and so on and so on. It's just getting bigger and bigger. It's going to infinity. If the value of R is less than or equal to -1, now the limit does not exist. Okay, and that's because if we look at it graphically in that case, as n gets bigger and bigger, what's happening is we might have a positive value initially, then it's going to be negative, but they're getting further away from the x-axis. They're bouncing back and forth, so they're moving away from the x-axis. They're bouncing back and forth. So we're not going to settle down to any value. Clearly, the limit does not exist. Okay, so that's just a quick review of what we talk about when we say geometric sequences. And you'll need to make a difference between geometric sequences and later on when we learn about geometric series. They're not the same thing. They're certainly related. Geometric series is just an infinite sum whose terms that we're adding up are a geometric sequence. Okay, so let's put all this to the test then. Here are some examples. Like, suppose I have the sequence with general term 7/8 to the n. Well, that's a geometric sequence, right? The first term is 7/8, the next term is 7/8 squared, then 7/8 cubed, and so on. So the value of R is 7/8, right? R is 7/8 in this case. Since the value of r is less than 1 in absolute value, the limit of this sequence is 0, and it's a convergent sequence. Here we have 3 to the n. So here the value of r is 3, right? Because 3 to the n, we'd have what? 3 to the first power is 3, 3 squared is 9, 27, and so on, 81, etc., right? And r is 3. R is greater than 1, so what's happening to the limit? It's going to infinity, and we have a divergent. The textbook sometimes talks about diverges to infinity. Okay, it's divergent sequence. C sub n, what about this? Negative 6/11 to the n. So our value of r is negative 6/11. So will this limit not exist because it's negative? We're bouncing back between negative and positive values, right? But hold on, right? It's still less than 1 in absolute value. So we've got that situation where we're bouncing back and forth, but they're going to get closer and closer to the x-axis as n increases. And so the limit again is 0. Again, anytime the absolute value of r is less than 1. So anywhere between -1 and 1, that limit will always be 0 for geometric sequences. Okay, of course, it's got to be a geometric sequence. Not all sequences are geometric, but this is going to be convergent. Here, notice I got -7.6, but this time that's the value of r, -7.6. This time the value of r is less than or equal to -1, and so our limit's not even going to exist. It's going to look something like this situation. It's changing between positive and negatives, but they're getting further and further away from that x-axis as n goes to infinity. So that limit does not exist, and of course this sequence is divergent. And then here E sub n is 4. Notice the value of r is equal to 1. Right, so this is the general terms would be 4, 4, 4, 4, 4, and so the limit as n goes to infinity, E sub n is going to be 4, and we're convergent. So there's an example of each type that we can encounter. So I hope that helps when you're dealing with sequences that are geometric. You need to remember how to determine their limit